For our last talk today, we have Raphaël Gomès with A Journey to Performance, using Rust in Mercurial. Raphaël will be taking questions in the Venulous chat throughout the talk as well as at the end. Raphaël is a Mercurial developer working at Octobus, a company that has collectively landed thousands of upstream changes and brought new user-facing concepts to the table. He had a hand in most of the Rust rewrite of some of Mercurial's internals, focusing on greatly improving performance. After a few years as a full-stack web developer for various private companies, he was convinced that a better calling for him was making free and open-source software that is fast and reliable. Mercurial is a distributed version control system mainly written in Python. While it is often the VCS of choice for monorepos, for its great scalability, certain parts remain slower than they should be. Over the past 2 years, an effort to rewrite parts of the Mercurial core in Rust has seen multiple significant wins in performance, even compared to C implementations. Thanks, Raphaël.
Hi, my name is Raphaël Gomès. I'm a software developer at Octobus. We're a small consulting company. We do mostly work around Mercurial, using Rust and Python and sometimes other things. Today we'll be looking into how we sped up Mercurial using Rust and some of the things we've done. But in particular, I'll be focusing on stuff that I'm aware of, more specifically because I've worked on it. So let's get started. For those of you who don't know, Mercurial is a version control system like Git or Subversion. It's distributed, so like Git. It's been started in 2005. Most of it is in Python. There have been C extensions for performance purposes for a good while now, and for the past 2 years or so, there's been Rust. I know that the number of lines is not specifically an interesting metric, but it gives you an idea of roughly where the amount of code is, I guess. It handles very big repositories. For example, the one from Mozilla is several times larger than the Linux kernel one. And it has a very powerful extension system that we won't be talking about really today, but is very interesting if you're into that kind of stuff. So I just said that we have about 40,000 lines of C code. Why did we start using Rust, and for what reasons? So the first reason is for maintainability. This is specifically for what I'll be talking about is specifically for the Mercurial project. It might not apply to you, but for us, Rust has just a better signal to noise ratio. By that I mean that a lot of the C code has a ton of stuff to do with memory management and the lack of quality of life features that Rust has, that makes it a little harder to read code. Even if you're an experienced C programmer, most of the C code has been written by kernel developers and so people that are quite competent at C. But even then, Rust gives us just more algorithmic code, if you will. It has better compile time guarantees. If you've heard of Rust, it has a lot of stuff around memory safety, so it's some sense of memory safety, but it pushes in the right direction. It's not a silver bullet, but it's better than C in that sense. And it has a standardized and modern tooling in the shape of Cargo, its package manager, Rustup, its version handler, I suppose, the test harness and all of that stuff. But one of the main reasons why we compare it to C is for performance. This is why we're here. It's compiled like C and has, well, no startup time because it's an executable. It has little to no runtime, so unlike Go or Java that will still be compiled languages, they have garbage collectors. Java has, well, mostly Java has a virtual machine, that kind of stuff. Rust is very, very low overhead, similar to C. It has zero cost abstractions, so I'm putting the air quotes and I guess literal quotes because they always have a cost, blah blah blah. But I suppose you've already had that discussion. Most of them are nice to have, like iterators, for example, and generics. And last but not least, multithreading is a lot easier to write in Rust. I'm sure you've all seen the joke. That's not really a joke, with a sign that is very high up on a wall against that's just saying you have to be this tall to write multi-threaded code. And with Rust, it's almost easy sometimes. You can still shoot yourself in the foot. It's possible, but it's a lot harder than if you were to do it in C or C++ or any other low-level language that I know of. And within the context of Mercurial, adding Rust allows us to attack Python from both sides. So the goal is not to replace Python. Mercurial is still very much a Python project, but using a compiled language with no other garbage collector allows for Python and Rust interop that is, while not trivial, easier than it would be, say, using Go, for example. So when I say attack from both sides, I mean that we can have both small extensions that look like Python modules that are called from Python but are really Rust code. So to speed up hot paths and small loops and that kind of stuff. And Python that is embedded in a Rust executable, so that we can have a Rust entry point. So the binary is a Rust one, and we can maybe, if we're looking for is the version or something, we don't have to start up a Python interpreter. Or if we know how to do an entire fast path without starting up Python because there's no extensions, it's a simple command and that kind of stuff, you can do it in Rust. That way it's a lot faster. That would be done. So for the first part, the embedding Rust inside Python, that would be using Rusty Python for now, which works quite well. And for embedding a Python interpreter inside Rust, we'll be using PyOxidizer, which is at first a packaging tool written in Rust by Greg, who's a maintainer for Mercurial, who's been a developer for years. But aside from its packaging benefits, it's also a good way of embedding Python in a Rust executable. But there are lots of things that we could talk about, but the thing I want to focus today on is aegis status, the command. So what it does and what we've done to make it go faster. So the purpose of the status command is basically to show what changed in your working directory from your latest commit. It needs to show possible values of modified, added, removed, etc. It needs to conform to ignore patterns in the form of hjignore files that are basically like git ignore or other ignore systems, just with different syntaxes inside, not just globs. And by default, it has to check every tracked file for changes, plus show the untracked files that are beneath the root of the repository and that are not ignored. So it's what we have to work with in terms of constraints. The output looks like this. If you have a modified, a new file, and an unknown file, it will show up this way. So last year, it ended last year, but I re-implemented parts of the dirstate. I'll go into what the dirstate is in Rust, which is basically a small part of what status is. I re-implemented the existing algorithm, the Python existing algorithm in Rust, and I used multithreading for traversing the working directory for a considerable speed up. And I've not created, it's not entirely my work, but we've used Rust and Python shared iterators. So I won't go into too much detail because I already have a presentation I've done at FOSDEM, 2 of them actually, on the subject. But the basic idea is we create a collection in Rust that is exposed to Python to look like a Python collection, and if we want to iterate on this collection, we need to share memory while we're iterating, so as to not copy the value and do some very weird synchronization across the FFI boundary. So that's what we did, and that allowed us to have good enough performance to justify adding Rust to the code base. So when I say considerable speed up, it's been reported to me by users, and I've also seen it in my own repositories, that it's about up to 4 times faster depending on what the repository is, the your machine is, how many cores it has, that kind of stuff. It's up to 4 times faster as the original AG status, which has Python and C. So it's now it's Python and C and Rust. It's available in CentOS and Gentoo, like the Rust version. You can compile it. I'm not aware of. I mean, maybe there's others. I'm not sure, but these 2 are the ones I'm aware of. We're using it on foss.heptapod.net. Heptapod is GitLab plus Mercurial. It's something that Octobus is doing. Also, the foss one is our free and open source free hosting service that we do for foss projects, and we're confident enough in the stability of the status code to have it turned on a hosting first service, which I feel is cool. And some Google employees that we work with that are either just contributors or maintainers of Mercurial have shown a strong interest in using this and Bioxidizer and that kind of stuff. I'm not saying that this is the official Google statement, it's just they've shown some good interest, so that's nice. Also last year, so February last year in 2020, I was at FOSDEM in Belgium, and here I was.
That's our target. That's what we're trying to achieve, but it is the unrealistic target.
So in the table, in the slide, I showed the difference between the experiment that Valentin Gatien-Baron, who's a developer at Jane Street, did to make a simple version of status that did most of the work, but not all the small variants that it's possible, just good enough for their case to see how fast they could go. And as you can see from this table, it goes from 2.4 seconds to 50 milliseconds, so there's obviously a huge gain. And I was saying that this target was unrealistic because it didn't do all of the things that status needed to do, and that it would just be like some sort of lower bound of what's possible. However, we've since redone a proof of concept. So when I say we, Octobus has done a proof of concept that turns out is even faster and does more. So it's not yet upstream, but this is what the performance looks like on a different repository. So keep in mind, this is not the exact same numbers, so because I don't have access to that repository. But on the Mozilla repository, which has about 250,000 files or something when I checked, here's the performance. So as you can see, ours our version is quite a bit faster. Even in the very pathological case that we had, it's a lot faster than either HG standard or the experiment of Valentin. So we're quite happy with that, and this is what we'll be talking about today. So first, let's go over how status works, basically, what it needs to do and that kind of stuff. If you were to do a very naive implementation of status, you would need to open all of the tracked files that you have and compare their contents to the Mercurial store. And if it changed, then you say, oh, it's been modified, it's been whatever. This is, of course, extremely naive and very much like just bad in terms of performance. So what the approach was for Mercurial was to have something called the dirstate. So I said I was going to talk about this. This is now. The dirstate is kind of the automatic staging area of Mercurial, if you will. It stores metadata about all tracked files. So the size, the exec bit, the mtime, and pretty much that's it about all the paths that were tracked. That way you can just compare it when doing a stat on the file system instead of having to open the file. This has existed since about 2005 or 6. It has a flat structure that hasn't been changed since then. It looks like this. So you have the two parent hashes to know where you're at in the history, and then an unordered and dynamically sized list, flat list of path plus the aforementioned metadata. So the old algorithm that goes with that structure is to first, this is very simplified, but this is the overall idea, is to walk and check the working directory, respecting the ignore rules. So if you go into a folder and if the folder is ignored, then you just don't walk it, and you gather all the results of any of the files encounter. Then if you compare those results to the dirstate, and if some of the files in the dirstate did not show up in the results, then you know they're either deleted, like from an RM or something, ignored, newly ignored, or under a symlink, because Mercurial does not follow symlinks for security reasons. There are many issues of this approach. It's the three main ones are that it's expensive to build the mapping of all of the things you've encountered, and to have to build a mapping for the dirstate. So when I say a mapping, it's either a dict in Python or a hash map in Rust, for example. It's in the tens of milliseconds or thousands of hundreds of milliseconds in big repositories. Just to, I think on my laptop, which is pretty recent, Mozilla Central took about 30 milliseconds to build the dirstate hash map. So it's quite expensive. So there you go. This is pretty expensive and bad. The ignore and security checks are quite expensive. So when I say the checks, it's whenever you have to recheck stuff that hasn't been in the first walk, you have to take a look at every single one of the parents of the path. So if you have A/B/C, you have to check that C is not ignored, but also that its parent B is not ignored and that its parent A is not ignored. And the security check, I mean, you have to check that every single one is not a symlink. So this is very expensive. And you end up potentially iterating more than once over the dirstate. So we need to do better than this. In order to do this, the dirstate had to change. So we needed a better data structure, and basically we needed a tree because we wanted to mirror the working directory and keep the hierarchical information that we need to have a more efficient algorithm. This having a tree allows for a unified iteration. So walking the memory data structure with the file system at once, you know which ones are you know if there's any divergence. If it's the same, then it's fine. If it's not the same, then you know what to look for. The ignore rules, as I said, are a lot more efficient because you just have that hierarchical information. Symlink substitution, much of the same, and nested repositories are very cheap to ignore because for the exact same reasons, because you don't have to guess where you're at, because you know exactly where you're at in the hierarchy. And if you want to do status inside a directory, so say you have a big monorepo and you just want the status of a small sub-project or something, that comes for free, because you can just look at the subtree. So this is pretty cool. So how exactly do we implement this? So we need a tree, but we don't just need a tree, because trees are slow. They're not that slow, but depending on what you want to do, they're pretty slow, because we want a memory a tree that is memory with good memory locality, basically. Because jumping around in memory is very expensive in general, and this is the first naive things I wanted to do had a lot of allocations and memory fragmentation that it was a lot more expensive than a hash map. It like 200 milliseconds instead of 30 or something. So we have the disk data first, which is the dirstate itself, the file containing the full nodes in whatever form that might be. That's not very important. And there's a vault, which is a Rust struct that has a reference to that data. We'll talk about more of that reference later. Which is basically how to handle the immutable side of things. So the things that are in the dirstate from the last commit. Then there's a vec of the paths that represents the mutable side of things, because this is not used only for status. This is used for other commands like add or commit or update. So there's a mutable aspect to it. So this splits into two types of nodes, two parts. There's the immutable and the mutable one. So both the on-disk node that you can see and the in-memory node are they go through the vault to interact with our paths. And since the on-disk node is just basically a pointer in a slot map, if you know what that is, this is just going into an index, so it's very cheap because it's just going straight to the data, because the vault basically just knows how to read the data itself. So the only allocation we need to do is whenever we have new nodes. Otherwise we can just have the data and read it lazily. So one important part of this is exactly how the backend storage is made. So we're using append-only storage, which is not new, but just for a small recap, you never overwrite data that you've written to. If you want to functionally overwrite something, you write after, basically. And whatever's reading that storage will know to skip or to just not go to the old data. So you end up with unreachable or dead entries and reachable or alive entries. And then whenever you want to update, you have the mutated or the new part that you just put at the end. That's how it works. It's been used, the append-only mechanism has been used in Mercurial since the beginning. The revlog is the base format of Mercurial that is used for its basic data structures, and it's an append-only format. It's a fixed size format, but this also works for dynamic size entries. A lot of databases use append-only storage, and since the dirstate is something that is not shared, that is not that we don't want to keep, it's just like a cache, basically, but not really a cache. It's a mix of different things. It's not something that it's truly append-only. Because once the unreachable parts become too large, we want to rewrite everything and discard whatever is not relevant anymore. This is usually called a vacuum for database storage. So in order to do that properly, we need to think about transactionality and multi-process stuff. So we use two files in the specific case of the dirstate, and also other cases in Mercurial. We use two files. The first one is a docket file, which contains metadata. It's very, very small. It contains whatever metadata the reader of the data file needs to read it properly. So maybe its size, maybe the offset of the root node to know where to start. But more importantly, it has the generation. Generation is a number that is unique to each vacuum cycle. So every time you need to vacuum or to rewrite the entire append-only storage, you change generations and you write to a new file. That way you never overwrite an old file. I mean, there can be cleanup later, but you don't do it at the same time anyone is using it. That way old processes can still point to the old data and that kind of stuff. So the docket is small enough to not cause any issues with transactionality, and we have ways of writing it atomically to disk. So this is basically this in conjunction with other locks ensures transactionality. Being append-only allows us to use memory mapping. So mmap, it works on Linux, it works on other OS. It's basically reserving chunks of virtual memory and pointing to it and lazily page faulting through the memory. So the nice side effect is that the memory usage stays the same with multiple processes looking at the same dirstate, for example, which is nice in server environments. If you have, I don't know how many connections you may have to a single repository, you don't need to spin up as much, so you reduce memory pressure, which is kind of nice. Since it's append-only, you don't have to worry about truncation, which is quite a big deal in memory mapping. If you truncate the data while the process is still reading it, it ends up with garbage kit data, which is potentially a security issue. I mean, it's not really a security issue because you still have assertions in place, but it's at least a functional issue. And the most important part of all of this is that it basically removes read time, because once you've done it, it's a tiny bit more expensive than just reading the file at first. But once you've done it, most of the time you'll just reread the same region of virtual memory, and it'd be free, basically. So, as I just said, mmap is basically free most of the time. To keep reducing the build time, which I said is very expensive for the tree, we chose to keep the full paths. So when you build a tree, you're very tempted to do prefix compression. So you have a/b/c, and you will store a, which shares the same prefix as a/b, which shares the same prefix as a/b/c. That way it's more memory efficient in the sense of disk space, but it's not memory efficient in the runtime sense of things, which by that I mean that every time you would need a full path, you would need to allocate a vec in Rust, or you need to do an allocation to concatenate into a full path, which is quite expensive when you want to do at least once per file, and you have hundreds of thousands of files. It adds up quickly. So we keep all of the paths in contiguous memory. All of them are full. That way we just never allocate unless it's for new nodes, which is pretty cool. There are other optimizations that we need to do in order to make it all fast. There's We'll talk about two of them. The first one is maybe it's work that we've done before this new storage backend, etc. It's just something that's very important because it gives us a lot of speed in execution. So because build time is taken care of mostly, you need a fast algorithm. So you need to traverse, because we're doing only one traversal, when you need to traverse the working directory as fast as possible. We have a recursive implementation. I tried doing an iterative one. The code gets a lot more complicated. It's not even faster. I mean, in the one that I've done, I stopped looking into it because it's not really worth it. I haven't never seen a repository that would potentially like explode the stack of either Python or Rust, so it doesn't really matter. The recursive implementation is a lot simpler. Right now, when it sees a repository, it spawns a task in a thread pool, which is kind of naive because we should be using like heuristics depending on, I don't know, size and that kind of stuff. And we've been seeing a lot of variance in repositories that have very imbalanced trees. So maybe that can go even faster. But this is, first step. It was fast enough. So we're using Rayon, which is a crate that gives us very good parallelism primitives, and it's sometimes so easy to use Rayon for iterating in parallel. It's extremely powerful. I encourage you to check it out if you don't know it. And we're using channels from Crossbeam channel, which they're inspired by Go channels, but they're very fast. It's not even showing up in profiles, so because we're doing so little, also the algorithm does not want to share more results than it has to. But Crossbeam channels are very simple to use. They're very fast, and since Rust has all of those memory safety checks at compile time, it works pretty much always, which is very cool. Well, it works now. That's what I meant to say. And the second thing that we've done to have a faster algorithm is mtime caching. So this is not something that is applicable all the time, and I'll go into the caveats in the second slide. But basically, the principle of it is you cache the mtimes of all of the directories in the working directory, and you compare it. When you walk, you compare the mtime to whatever's on disk. If it's different, it means that you need to read the dir. So because the mtimes, this relies on the fact that the mtime should be updated if one of the direct children of the directories is removed or added. Otherwise, you need to just add the children, because we already have the list of what's interesting to us, and then we recurse, because we keep the directories also in memory. So we can even cache unknown or ignored files, because the only thing that matters about them is whether they exist or not, which allows us to save expensive reading of the directory and just do stats. So this turns out to be quite a lot faster. Of course, this only works for certain OS file system pairs, so you have to be careful about this, because sometimes it's flaky and not reliable, so you have to keep a very tight list of whatever works. But if you have a huge repository with, I don't know, hundreds of thousands or millions of files, and you have performance problems, maybe don't put it on FAT32. It needs, like any other cache, it needs to be properly invalidated. If the parents of the working directories have changed, if you've moved file systems, because that may happen. If there's a new ignore rule, that kind of stuff. So let's recap. We need to build the tree first and foremost. We need to build the tree. So you open the docket file, you read it. It gives you the right data file corresponding to the dirstate. So you mmap the data file. It's probably already been mmapped. The vault already knows how to access the data, and it does not need to read it first. So it just, you say, just reference that point, and then you can just jump to whatever node you need. And the root node is given by the docket. So it's exactly what I just said. It already knows where to point. Then you need to check the working copy. Again, this is very simplified, but this is the overview. You iterate over both the dirstate and the working copy at the same time. You check for any divergences, any difference in state for any directories, or etc. If you use mtime caching, which it will be optional, by default, we haven't decided, but basically there will be an option for that. If you already do mtime caching, you already need to stat the directories, so you get the symlink check for free. So the one where a directory becomes a symlink, that comes for free because the stat call will tell you what kind of node it is. So that's, you get 2 for the price of 1, which is kind of cool. And then you send the results from all threads to a channel, and you collect them, and that's it. So just to recap, the performance that we've seen in our new proof of concept that does most of the work. When I say most, it's that we need to fine-tune, see the edge cases, and write more clean code, but it does what it needs to do in terms of what's expensive. This is what the performance looks like, and it's very encouraging. So, as I said before, the dirstate is used in many commands. It's used in commit, in diff, in update. So update is like checkout is when you move in the revision history. Purge, which is used by CI systems a lot. Files, which looks at what the files are at any given revision. It's used in many commands. So this work here is not only done for status. All of the dirstate work will trickle down to all of the other commands, which is quite nice. Since this is the LCA, I want to talk a little bit about the difference between all of the platforms and why I think, as a developer, Linux is the simpler platform for developing Mercurial. On Linux, paths are just bytes, plain bytes. So there's no Unicode normalization, there's no conversion, there's no nothing. You just have bytes, and you can use them as is. If you're on another OS, you might need to do an allocation every single time, or double the whatever memory you need, because you need to store the normalized version, or that we'll need to do that at some point. So that's very much simpler in Linux. We have great file systems like Btrfs. It's the one we use at Octobus. It's like you get some very nice deduplication stuff. You get nanosecond precision mtime, which saves us a lot of expensive lookups if we're unsure of whether the mtime has been cached correctly because of the last time we run the AG status or that kind of stuff. On macOS, there's Unicode normalization issues, there's case sensitivity issues. So there was, for example, a bug in both Mercurial and Git, and potentially others, I suppose, where you could attack the repository by having .hd but in capital letters, and however HFS plus works means that you would gain priority over the lowercase .hg, and it wouldn't be considered a conflict. So it's just pretty terrible. On Windows, you have similar issues as Mac OS and more. And the file I/O is quite slow, and it has a lot it has more footguns regarding transactionality and M mapping and that kind of stuff. So for one example, a few years ago, well before I was involved at all, file I/O in Windows was so slow for closing files that Mercurial started having a separate thread to send all the close calls to, so that the process would terminate a lot faster, because Windows does a lot of stuff regarding antivirus software and all of this. I believe that there's a talk last year at LCA about a Rust up maintainer that talks about this very issue and then how they fixed it, and they mentioned Mercurial, so that's funny. But it's clearly a lot easier to just work in Linux. There's a lot fewer footguns. It's out of the three, it's the easiest one if you do a lot of I/O and file system stuff. With that said, Linux is fast, but it could be faster. It could be simpler from a developer perspective. So, for example, whenever we need to actually read a directory entry, we do the open dir, then read dir loop, then close dir, and it looks to be quite slow, just because of context switching, but also maybe the Rust implementation of read dir is kind of expensive. I haven't looked into it, but Valentin told me something about this, so I should check that out. But maybe using directly the underlying syscall, which is the getDents, could be faster. I know that there's a lot of async IO uring stuff that's coming to Linux, and while this is not really an async problem, maybe IO uring will give us some batching stuff that is better. So we'll see. A lot of our time is spent in system time instead of user time, which means that we've done a good job, but maybe the system could be faster. So if any kernel developers or enthusiasts have ideas, they're welcome. And maybe we could use statat and openat, because it may be faster to give directly the parent directory. That way the kernel, or the file system rather, does not have to rewalk the tree at the same time. And I want to just finish with by saying that Mercurial is always getting faster. This is not the only thing that we've done. It has a good history of getting improvements to its speed and handling very large scaling. We have other Rust endeavors that we've done. So, for example, ancestor iteration, which is when you go back up in history, leads to 3 times faster performance when pushing or pulling. So when you have to check what changed between 2 repositories. Copy tracing, which is checking renames, etc. So it's a lot faster. And sorry, I just bugged out. Node map. So this is like a micro benchmark. I don't have really much time to get into it, but basically there's a lot of stuff that's been done for micro stuff that has good impact overall. I don't have time to explain the node map. hjcat and files, which are the 2 commands. Cat will show you the contents of a file, and files will show you how many files you have. Well, not how many. The list of files at a given revisions are more than 10 times faster. And non-Rust development also occurs. So cloning needs 40% less memory, which is very cool because performance is not just wall time, it's also memory efficiency. There's been some pretty catastrophic explosion of manifest size that has been thwarted with the new Revlog format. We have a newer Revlog format that is coming up that should fix a lot of the performance issues that we have regarding like too many files and that kind of stuff. And people do a lot of branchings. We have a new branch cache that is coming that is going to make a lot of things a lot faster. So keep an eye out in the next few months. We'll do some stuff on Twitter or on the Mercurial website. So yeah, keep an eye out for new stuff. Get up to date, and thank you for listening.